Hey guys, here's a video talking about writing equations for polynomials and then about polynomial models. I wanted to give you some background on this. I'm not sure if we're going to have school over the next couple days, and this is going to be your assignment if we don't. Or it's going to be homework over the next couple days to a week if we do. So the first part is writing a polynomial function of least degree. So we've got a couple things to digest here. The first is polynomial function. This is probably going to be in factored form, so that we can work with this a little bit more easily. Least degree means we're not going to have anything squared or cubed unless we have some specific information. And then the other piece of this is integral coefficients that have the given zeros. Integral coefficients is going to come into play if we have any fancy zeros. We're going to have some ways to deal with that. That means that we don't want any decimal fraction, square root weird coefficients that go with this. It's actually being a really straightforward process for a lot of these ones. It's going to be based on the idea that if we're given zeros, we can figure out factors based on those zeros very quickly. The first thing that we have to know is that if these three, 1, -1, and 2, are zeros, by the remainder and factor theorems, that tells us that x minus 1, because if I plugged in 1 I'd get 0, x plus 1, because if I plugged in -1 I'd get 0, and x minus 2, because if I plugged in 2 I'd get 0, would be my factors for that. In fact, you're done. This is it. This is as far as you need to take this. The understanding is that you could multiply this out if you wanted to, but all we're trying to do is to create something that we can type into some kind of graphing program and get a graph out of. And this will work just fine for that. For the second one, we've got 4 different zeros, but the process is still going to be the same. So we've got x plus 3, x minus 5, x plus 4, and x minus 3. And again, you could multiply that out, or you could leave it like that, and that would be totally fine. This would be in factored form. I'm going to jump ahead to number 6, because here we've got ones that are going to give us fractions unless we do something special. So we know that if -5 over 4 is equal to x. If I want to get this into something equals 0, what I can do is kind of undo the process that I used to get here. So it's like you're unsolving this equation. I'm going to multiply both sides by 4. So we get -5 is equal to 4x. And then if I add 5 to both sides, that gives us a term on the right of 4x plus 5. And just like before, we could just use those opposite numbers here. We have to do a little bit more work to get there, or you might be able to realize that the denominator ends up being multiplied by the x, and the numerator ends up being added in its opposite form. So -5 over 4 would give us 4x plus 5 as a factor. -5/3. I'm going to do this longer process out again just so we can see how to do that. So -5 over 3 is equal to x. If I multiply by 3, I get -5 is equal to 3x. And then if I add 5 to both sides, I get 0 is equal to 3x plus 5. And that's my factor. I guess I can show you that you could do the same thing using any of these terms. So -4 is equal to x, and if I add 4 to both sides, we get 0 is equal to x plus 4. So that gives you the factor for that as well. But for simpler ones, it's usually not a necessary thing. This would be my final answer. I'll also talk about number 7, because here we have multiplicity. Multiplicity 2 means that whatever this factor is, it's going to be squared. Same for this guy. Multiplicity 2, that's going to be a squared factor also. That's just a reminder that multiplicity can help us determine what's going on in a function. Okay, if we've got 4, that's going to be x minus 4, and if we've got 3, that's going to be x minus 3. I'm actually going to jump down to number 13 for a second because this will talk about something that's important. When we have either imaginary or radical values, we have to include some other stuff. So if negative I, for example, is a root, that would mean that x plus I would be a factor. And if square root of 7 is a root, that would mean that x minus the square root of 7 is going to be a factor as well. But this doesn't fulfill what we need to talk about as far as those integer coefficients. Because if I were to multiply this out, and let's see what would happen, we get x squared. Okay, we're good so far. We get negative square root of 7x, oh boy. We're going to get plus ix, that's even worse. And we're going to get a plus I square roots of 7, minus I square roots of 7. That's even worse than worse. The good news is we have a way to avoid this, and we've already done a bunch of the math that really results from this. And once you understand what's going on here, it ends up being a pretty simple process. The idea behind how we're going to work on this is going to be based on conjugates. And the big idea here is if, for example, x minus the square root of 7 is going to be a factor, and I have to have integer coefficients, that means that x plus the square root of 7 also has to be a factor. I'm going to multiply this out so we can see why this is true. We get x squared. We get plus the square root of 7x. We get minus the square root of 7x. And we get minus, well, the square root of 49 is going to be 7, which simplifies to x squared minus 7. You might notice this is kind of like, or it is difference of two squares, but with a non-square number. We end up with plus and minus the square root. If the square root of 7 is a 0, in order to have an integer coefficient, the negative square root of 7 also has to be a 0. So whenever we have 1, we have the opposite. The same exact thing is going to be true for that I term. If x plus I is going to be a factor, the only way to get rid of that I in my final answer is to have x minus I also a factor. And when we multiply this through, we get x squared minus ix plus ix, those cancel out, and negative I squared, which is negative negative 1, we get x squared plus 1 is my other term there. I'd like you to, again, notice if we include that conjugate, the I pieces cancel out, and we're left with something that's okay for us to work with. The same rule is going to apply here. If I ever have an imaginary root, the opposite of that root is also going to be part of that problem. So we end up with 4 zeros that we can work with. Not just x plus I, but x minus I has to be part of that too. Not just x minus the square root of 7, but x plus the square root of 7 has to be part of that as well. I chose this one because it let me talk about both of these things simultaneously, and some of the other problems are way more complicated, but they only talk about one of those. Let's go to a couple of those now. Let's talk about number 9. So number 9 has 4 really messy looking roots. We've got negative 2 plus the square root of 2. We've got negative 2 minus the square root of 2. We're going to look at this the same way that we did before. One of the interesting things here is that if I look carefully at my first pair of roots, I notice that this is negative 2 plus a square root, and this is negative 2 minus a square root. These are already conjugates. And because I have both of those pairs, I don't have to add any additional roots. The same is going to be true for my next two in this case, where I have 1 plus my radical term and 1 minus my radical term. And just because those happen to be conjugates, we can treat this as, I'm going to use parentheses so I don't have to deal with changing negatives around. So negative 2 plus the square root of 2. We've got x minus negative 2 minus the square root of 2. This is going to be really ugly, but you're going to be done as soon as you write this down. We're going to have x minus 1 plus 2 square roots of 2. And x minus 1 minus 2 square roots of 2. And again, you're done at that point. You could multiply this out, but it's going to be a horrendously, terribly, awful answer. Let's do one more of these. Number 11. Once again, I know that I need to include some conjugate roots here. If I've got negative 1 plus 3i, that also means that negative 1 minus 3i has to be a root. And if I've got negative 2i, it also means that plus 2i has to be a root. I can build my polynomial from this. So x minus negative 1 plus 3i, x minus negative 1 minus 3i, x plus 2i, and x minus 2i. And again, I'm done at this point. In number 19, we're talking about designing a box. This is one of the only really easy polynomial model type equations. It's also really boring, and you're going to see it over and over again, and every one is basically going to be the same exact problem. In fact, you're probably going to have one of these on your midterm just because they're easy for us to put together. So this is a really good one for us to practice. So we're designing an open box container. What that means is that we have a box that doesn't have a top. It's going to be storing really awesome stuff. That's obviously an important part of this problem. It'll be made by a piece of cardboard that's 10 inches by 15 inches and formed by cutting squares out of each corner. Let's talk about what that looks like. In fact, part A asks you to draw a piece of cardboard. Use my mad artistic skills. That's going to be 10 by 15. Cutting squares out of each corner and folding up the sides. So in other words, I'm going to cut 4 squares, and I would fold up the sides along these dotted lines in order to make that box. I've got lots of examples of boxes made in this fashion from my pre-calc class, kind of sitting in the back of the room if you'd like to see one. I know it's very exciting. Write expressions for each side of the box. Okay, well, I need to figure out some things. I don't know how big those squares are, so I'm probably going to call those x and x. If this whole side was 15 and I'm cutting x away from both sides, that means that length is going to be 15 minus 2x. And vertically, I'm going to end up with, so that's this side, 10 minus 2x because I'm cutting an x away from both sides. Okay, so each side of the box, so if I've got a box we need a length, a width, and a height. So I might just arbitrarily say that the length is 15 minus 2x, the width is 10 minus 2x, and then the height, okay, well that looks like this. Oh, that's the folded up corner, so that's going to be x. Write an equation to describe the volume of a box. Hopefully that we know that a box is really a rectangular prism, in that volume is length times width times height, but we can do better because we have expressions for those things. So my volume is equal to 15 minus 2x times 10 minus 2x times x. Okay? Use a graphing calculator in Desmos to find the maximum volume. How long should you make the cuts? What is the maximum volume? What should the dimensions be? That's a lot of stuff going on here. So maximum volume, that's going to occur when I'm at the highest V. And why not just call that Y just for the sake of ease? I'm going to graph this on Desmos and import the screenshot here so we can see what that looks like. Okay, I've imported the graph from Desmos. I literally just graphed those three factors as an equation, and then I zoomed so it became a little bit more appropriate. Somehow that volume got stuck to this, so we'll keep it there. And what we're talking about is the maximum here. I'm also going to talk a little bit about some of these important pieces. I'd like us to remember that the volume equation was 15 minus 2x, 10 minus 2x, and x. And we got that because it's a 10 by 15 piece of cardboard. The first thing I'd like to talk about, even before I talk about that maximum point, is numbers that make sense for this graph. I'm going to argue that the only numbers we can use are between 0 and 5. That's what we call the domain of this situation. And the reason that we can't go above 5 is if I try to cut a 6-inch square from a corner, well, if I cut two 6-inch squares from a 10-inch corner, we end up with a negative side length, and that doesn't make sense. That's why we have this area that has negative volume down here, where we have volume being the height, and that would be something that we have to consider if we're looking at a graph and trying to interpret something. We also can't cut negative squares, so the negative side of this graph doesn't even make sense. So again, the only part of this that we really care about is this area along between 0 and 5 for x values. Without calculus, we can't do a heck of a lot in terms of algebraically finding a maximum for anything besides parabolas. We know this would be the vertex if this were a parabola. But we can do this graphically. And on Desmos, we can literally just touch the point and that comes up. That means that we should cut a 1.962 inch section out of my box. That means that my dimensions are going to be, so it's 15 minus 1.962 times 2. So the length is 11.076. The width would be the same thing, but 10 instead of 15. So that'd be 6.076, and the height would be that 1.962. The volume for this would be the height here, or 132.038. What you're going to find is that all of these boxes are pretty much going to be set up in the same way. Number 20 asks you to look at the same type of thing, but with the chance of drawing perhaps two boxes. So looking at one box, this might be 20 by 30, and we're going to do a similar thing, folding up the sides. If you cut this into two pieces of cardboard, you'd start off with a 20 by 15 and two of those, or if you cut hot dog way instead of hamburger way, you'd go 30 by 10 and have two of those also. The rest of this is going to be really similar to what we did for number 19.